Bismillahirrahmanirrahim and Assalamu alaikum. Welcome to our YouTube channel Paper World, where we are solving past paper questions of IGCSE Physics 0625. And today we are going to solve paper 4, which is a theory paper for May, June 2025. So the variant is P43. Let's start. But before we start, kindly like and subscribe the channel. Okay, question number 1. A car travels at a speed of 20 meters per second. The driver applies the brakes when he sees a red traffic light. Figure 1.1 shows the speed time graph for the car. Okay. Determine the speed of the car at time is equal to 2 seconds. Acha, let me just lower the magnification so that we can see the question and the graph together. Okay, so the first part was to determine the speed of the car at t is equal to 2 seconds. Okay, now the speed is mentioned over here, the time is mentioned over here, so this is t is equal to 2 seconds, and we are going to draw a line, a horizontal line like this, and then we are going to see that where does it correspond to on the y-axis where speed is mentioned. Okay, so let me draw the line and come back. Okay, so I drew a horizontal line at time is equal to 2 seconds up till the curve of the graph, and then I drew a line which was vertical, and here we can see that 1 square is equal to 1 meter per second. So this actually would be 11.5 because it's a little more than 11. So the speed of the car at time 2 is 11.5 meter per seconds. Okay, so this was pretty much clear and simple. Okay, the B part states that calculate the distance traveled by the car between time 0 and time 4 seconds. Okay, the time was 4 seconds for the entire journey. So we know that in a speed time graph, this line represents the gradient basically of the graph represents acceleration or deceleration, and the area that is under the line basically gives us area. So if we see that, we can draw and divide this area into 2 parts. Okay, so this can become a rectangle, and then here we have a triangle. So we know what the area, how to find the area of a rectangle. Area of a rectangle can be found by the formula length into width. So the length of this rectangle is 20, and its width is 0.5. 1, 2, 3, 4, 5. Yes, this is 0.5. So 20 into 0.5 is going to give us 10 meter squares, and then we are going to go and move towards this area, which is in the form of a triangle. So we know that the area of a triangle basically is depicted by the formula half base into height. So the base of the triangle would be 4 minus 0.5, that is 3.5, and the height obviously is the same, which is 20. So this is going to give us an answer of 35 meter squares. Okay, so now we have the area of this rectangle and of the triangle as well. So we've covered all the area that was there under the graph. So to calculate the distance, we are going to add 10 and 35, and this is going to give us an answer of 45 meters. Okay. Okay, moving on to part C. Calculate the deceleration of the car between time 0.5 seconds and time 4 seconds. Okay, I just told you that the gradient of this line gives you acceleration or the deceleration. So they've asked us to find the deceleration between between time is equal to 0.5 seconds and 4 seconds. So we have to take the area of the graph that's between 0.5 and 4 seconds. So we can take this area, and we need 2 points over here, since we know that in order to find the gradient we need 2 points on the x-axis and 2 points on the y-axis. So 1 point we can take this, which is 4, and the y, the reading corresponding value on the y-axis is 0. So this is 4 and 0, and then we can take this point over here, which is 0.5 for x-axis and 20 for y-axis. So let's take this to be x1 and this to be y1 and this to be x2 and this to be y2. So let's find the gradient that is going to be found by the formula y2 minus y1, x2 minus x1. So our y2 value is 20, and the value for y1 is 0, and the value for x2 is 0.5, and for x1 is 4. So this is going to give us 20 by 3.5, and obviously negative 3.5 because this is deceleration. So the answer is going to be minus 5.7 meter per second square, and this minus can be ignored since it's just telling us that it is deceleration, negative acceleration, and not positive. So the answer that we are going to get is 5.7 meter per second square. Don't forget the units. Okay. Oh, so moving on to question number 2. The space vehicle is moving at a velocity of 7,800 meter per second. The mass of the space vehicle is 840 kgs. Show that the momentum of the space vehicle is approximately 6.55 into 10 raised to the power 6 kg meter per second. Okay, we've got to find the momentum. So we know that the formula for momentum is mass into velocity. So we have been provided with the mass, which is 840 kgs, and we have been given the velocity, which is 7,800 meter per second. So multiplying this is going to give us an answer of which is actually equal to 6.55 into 10 raised to the power 6 kg meter per second. So we've reached this answer, and that was what we were supposed to do. Okay, so moving on to part B. It states that the capsule ejects the nose cone as shown in the figure. Okay, now the nose cone is separate. Determine the velocity v of the capsule after the nose cone is ejected. Give your answer to 3 significant figures. Okay, now we've got to understand that according to the law of conservation of momentum, the momentum in an isolated system, the total momentum is conserved because it can neither be created nor destroyed. So momentum before collision or momentum before a certain action is equal to the momentum after the collision or after a certain action. So if we know this concept, we know that there is going to be a momentum which was there before this nose cone got separated. Okay, so that is going to be m1 and v1, and this was single entity at that time. Now it has transferred into 2 entities. Okay, so now mass of the first one into the velocity plus mass of this second thingy into its velocity. Okay, so m1 v1, we already know that before anything happened, the momentum was 6.55 into 10 raised to the power 6 kg meters per second. And after that, now we know that the mass, the first mass is 720 kgs, and we don't know its velocity. And the other mass is 120, and its velocity is 7850. Okay, so this is going to remain over here, minus 120 into 7850 divided by 720 is going to give us the velocity, v actually. So after we are done with all the calculations, we get the velocity to be, and we've been told that we need 3 significant figures. So this is 8. So this is going to get increased by 1. This is going to get 0. So this is our velocity. Let's write it in the answer place. Okay. So that is how we determine the velocity v of the capsule after the cone is ejected. Okay. I hope you understood that. See, a different space capsule returns to Earth. Figure 2.3 shows this capsule just before it lands in the sea. The capsule travels at terminal velocity. Okay, the upward vertical force acting on the capsule is 120 kilonewtons. Calculate the mass of the capsule. Okay. Now we know that in order to find the mass, what we need is our formula F is equal to ma. So force over here is 120,000 newtons. Mass, we don't know. And as it is moving at a terminal velocity, so the acceleration that is going to be acting on it is going to be 9.8. Okay. So after we divide this with 9.8, we will get a mass of 12,000 kgs. So the mass of the capsule is, okay, so it's a fairly simple question. Question number 3. Figure 3.1 shows an archer aiming an arrow at a target. The archer pulls back on the bowstring, doing a total of 110 joules of work. Her hand moves a distance of 0.45 meters. The bow is bent and stores energy. Show that the average force applied by the archer in pulling the string back is approximately 240 newtons. Okay. Now we've been given work and distance. So we are going to use our formula work done is equal to force into distance. So work done is 120 joules. Force is something we have to find, and the distance is 0.45 meters. Is going to give us a force of 244.4 newtons, which can be rounded off to 240 newtons. So we've reached our answer. Okay, moving on, the archer releases the bowstring. All the energy in A is transferred to the arrow. The arrow moves off with an initial speed of v. The mass of the arrow is 0.030 kgs. Calculate the initial speed v of the arrow. Okay, now we can see that when the archer is pulling the arrow, so there is a string over here. So basically she is gaining elastic energy, and when she leaves the arrow, this elastic energy is converted into kinetic energy. Since the arrow is now in motion, and the law of conservation of energy states that the energy can neither be created nor destroyed, it is just converted into another form. Okay, so the initial energy that we had was 110 joules. Okay, and now the energy is transferred to the arrow, so that means that kinetic energy is equal to half mv square. We've got to use this formula. So 110 was the energy, half mv square. So 110 is equal to half 0.030 v square. 110 into 2 by 0.030 is equal to v square. So this is going to give us an answer of 7333.3 v square. And since we just need v and not v square, so square root of this number is going to give us an answer of 86 meter per second. Okay. Part 2. Explain why the speed of the arrow as it hits the target is less than the value in B part 1. Obviously, all of the energy is not converted into the other form of energy. There are losses. Some energy may be lost to the surrounding. There might be air resistance present. So the speed of the arrow as it hits the target would be less than the estimated one. So we can write that some energy may be lost to the surrounding. Or maybe that there is air resistance present. You might write any one of these reasons or any other that is a valid reason and you can think of it. Question number 4. Figure 4.1 shows a pan with a copper base on a hot plate. The hot plate heats the pan and the water. Explain how thermal energy is conducted through the copper base. Okay, now we know that copper is a metal and it is a good conductor of heat as well as electricity. And why is it so? Because copper or other metals as well have free moving electrons and they can take the heat as well as electricity and transfer it. Okay. So first, this is how thermal energy is conducted. Secondly, copper pan is a solid, and we know that in solids the lattice arrangement is such that these molecules vibrate in their mean positions. Okay. So that is how when all of these vibrate, get heat, get more kinetic energy, and all of these vibrate, that is how the energy can be conducted through the copper base as well. So I'll just write the answer and we'll go through it. So you can write copper is a metal and metals are good conductors of thermal energy as many of the electrons in metal conductors are free to move. They carry thermal energy as they get hot and move through metal. Lattice ions also vibrate and cause their neighboring ions to vibrate as well, transferring energy. So if you write both these reasons and explain them, you are going to get your 3 marks. Acha ji. Part B, the first part, define in words specific heat capacity. Okay. Specific heat capacity is defined as the amount of energy needed to raise the temperature of 1 kg of a substance by 1 degree C. ठीक है जी. And its formula is delta E by m delta theta, which is the change in temperature. Okay, part 2. A student heats a metal object at 100 degrees C. The student places the metal object in an insulated cup containing water at 22 degrees C. The final temperature of the water and the metal object is 31 degrees C. The specific heat capacity of water is 4.2 joules. The mass of the water in the insulated cup is 50 grams. The mass of the metal object is 54 grams. Calculate the specific heat capacity of the metal. Okay. So we've been given the specific heat capacity of water. We've been given the mass of the water as well. We've been given the temperature of the water and the final temperature of the water and the metal as well. So the first thing that we need to do is that we've got to write metal and water. ठीक है. So specific heat capacity of the metal is something we've got to find. ठीक है. Mass of the metal has been given to us as 54 grams, and delta T would be the final temperature and the initial temperature. So that is going to be 100 minus 31 degrees. Okay. So solving this is going to give us an answer of 3726. Okay. Now we are going to look at the water side. Sorry. Oh, sorry. This is energy is equal to Cm delta T. I didn't write that. I should actually. Acha. Energy over here. C we know is 4.2. Mass we know is 50. Delta T is going to be 31 degrees minus 22. So this is going to give us an answer of 1890. So C is going to be, once we have both these energies, so C is going to be 1890 by 3726, and this is going to give you an answer of 0.507 joules or gram per centimeter cubes, whatever you like. Okay, so there are many ways of doing this question, but I actually find doing this method the easiest. You can find everything and then equate them together. Okay, so if you have a better way, kindly use that and do that. Okay, question number 5. Figure 5.1 shows dense medium. That is why ray S is being totally internally reflected, and the other one is that the angle of incidence is greater than the critical angle. So that is why ray S is totally internally reflected. Okay, so these two conditions have to be met for total internal reflection to happen and for a critical angle to be made as well. Okay, question number 6. Ultrasound is an example of longitudinal wave. Yes, obviously it's a sound wave. Define the term ultrasound. Okay. Any sound which has a frequency of more than 20,000 hertz, that is a limit that humans can hear, is defined or termed as ultrasound. So any sound with a frequency more than 20,000 hertz is described to be ultrasound. Okay. Part B. Describe what is meant by a longitudinal wave. Okay, a longitudinal wave is a sound. Is a wave for which the particles of the wave vibrate parallel to the direction of the motion of the wave. Pretty straightforward. Part C. Ultrasound is used to locate objects below the surface of the sea. Describe how ultrasound is used to locate an object below the surface of the sea. You may draw a label diagram as part of your answer. Okay. Let me write the answer because it's going to be a long one, and then I'll just explain. Okay. Sonar basically is the method used to locate underwater objects. For that, a pulse of ultrasound is sent down from a boat and it reflects either from the seabed or the object that it has to locate. And the time taken for the reflected pulse to be received is measured. It is used with the speed of sound in water to calculate the depth of the object, or sometimes the depth of the seabed, whatever. Over here it's mentioned that there was an object, so we should stick to the object. This is the diagram that you can draw. In one diagram the pulse is going, and in one diagram the pulse is being reflected, and we can show it with the help of these arrows, and this is how you are going to write it. Okay. And part 2, state one other use of ultrasound. Obviously, one use of ultrasound is to scan soft tissues of the body. Organs, soft tissues of the body. Okay. Moving forward to question number 7. 7. A student sets up the circuit as shown in figure 7.1. Part A, determine the value of the current measured by the ammeter. Acha, my suggestion is that you just read the circuit first, understand it, and then start doing these parts. And as you keep on doing these parts, and as you keep on finding the unknowns, keep on updating them on the circuit diagram. So for example, this is a circuit which has an EMF of 12 volts, and this is a series circuit with two components connected parallel to one another. So we must know that in a series circuit there are two principles, that current throughout the circuit is the same, right? And the voltage across every component is different. Whereas for a parallel circuit, the current is different for every component, and I total is this, and the voltage across all the components is the same, right? So we know this. So once we know this, we know that this is there is an EMF of 12 volts, and there is a current of 0.50 amperes generated in the circuit. So it's going to go here, and then it is going to go here, pass through this resistor. The current is going to change, but once it passes through, the current is going to be the same, and then it reaches this junction where some of it is going to go to resistor R and some of it is going to go to the 20 ohm resistor. If both of these resistors were of equal resistance, then this current would equally divide among these two resistors. So some value of current is going to go through these resistors, and when that current is going to come to this junction, so it's going to be 0.50 amperes again. And then it goes down and over here passes through this ammeter and reaches the other terminal of the battery. So they've asked us the question, determine the value of the current measured by the ammeter. So this ammeter is going to measure the value of the current to be 0.50 amperes because of what I've just told you. Okay, part B is calculate the potential difference PD across the 6 ohm resistor. So to find the potential difference, we need two things. V is equal to IR. We need the current and we need the resistance. So current, we know that the current that is going to enter this resistor is going to be 0.50, and the resistor is 6 ohms. So 6 into 0.50 is going to give us an answer of 3 volts. Okay, so this resistor has a PD of 3 volts. So this means that if this resistor is taking up 3 volts and the total EMF is 12 volts, so the voltage that is going to come after this resistor is going to be 12 minus 3 is equal to 9 volts. So this resistor is going to get 9 volts and this resistor is going to get 9 volts as well, since they are connected parallel to each other, right? So that's how we've updated our circuit. Now they're asking us in part C, show that the PD across the 20 ohm resistor is 9 volts. So we've already done that. But how are we going to do this? That we know that the EMF, this do it like this, V1 plus V2. Okay, it's 12 volts. V1 we know is 3 volts and V2 we still want to know. So 12 minus 3 is going to give us 9 volts of V2. Okay, the resistor that has a resistance of 20 ohms has a voltage of 9 volts. How? We've stated that, and you already knew that when we calculated it over here, right? So it became simple for us. Part D states that calculate the resistance of resistor R. So this is the resistor R. We first need to know that what is the current that is going into resistor R, because we need V is equal to IR. We know the voltage, we need to know the current, and then only we will be able to find the resistance of this resistor. So over here, for this resistor, we already know the voltage and the resistance, so it is going to be very easy to find the current for this resistor. So we are going to do that first. And why are we doing that? I'll just tell you in the moment. 9 volts and 20. So 9 over 20 is going to give us an answer of 0.45 amperes. Okay, is I. So if we return to the circuit and we know that this resistor is getting 0.45 amperes and the total current here was 0.50, so this is going to get a current of 0.50 minus 0.45. This is going to give us a value of 0.05 amperes, right? So now we know the current, we know the voltage, so it is very easy to find the resistance. V is equal to IR, 9 volts, 0.05 amperes of current, and R. So 9 divided by 0.05 is going to give us an answer of 180 ohms. So the resistance of the resistor is 180 ohms, right? So this is our answer. So you see that if you keep on understanding the circuit and solving the questions become easier. If you have an understanding of the circuit, though, the question becomes easy, otherwise it becomes difficult. So moving on. Okay, question number 8. Part A, state what is meant by an electric field. Electric field is a region where an electric charge will experience a force. So it's a region where an electric charge will experience a force. Okay. Part 2, figure 8.1 shows a negative point charge. Draw 4 field lines to the pattern and the direction of the electric field due to a negative point charge. Okay. These can be 4 lines and the direction would be inwards, since negative and positive charge attract each other. If this was a positive charge, then the direction would have been outwards. since positive charges repel each other. Okay. Part B, the potential difference PD of the lightning strike is 2.9 into 10 raised to the power 8 volts. The energy transferred by the lightning strike is 4.5 into 10 raised to the power 5 megajoules. Calculate the charge that flows. Okay, the formula that unites all these entities together is V is equal to W by Q. So V we know is 2.9 into 10 raised to the power 8. And W we know is 4.5 into 10 raised to the power 5 into 10 raised to the power 6 because of this mega thing. Mega is 10 raised to the power 6 and Q. So Q is going to go there and 2.9 is going to go come over here. And after we've calculated, so we get a charge of 1600 coulombs. All right, so let's move to part C. The current in the lamp is 2 amperes. The lamp is switched on for a time of 120 seconds. Calculate the charge that flows. So this is going to be solved by the formula I is equal to Q over T. So I is 2, Q is something we need to find, and this is 120. So 120 multiplied 2 gives us a charge of 240 coulombs. Okay. So this is done as well. Question number 9. Figure 9.1 shows a transformer. There is an alternating current in the primary coil. Describe how an alternating current is produced in the secondary coil. Okay. Now, if we know the principle of transformer, we know that the primary coil has alternating current in it. So this creates an alternate magnetic field. And this soft iron core transfers this magnetic field to the secondary side. Over there, the secondary side basically becomes a conductor in a magnetic field, and when it becomes a conductor in the magnetic field, a current is induced in the coil. So this is how the alternating current is produced in the primary coil, is transferred to the secondary coil. So let me write the answer over here so that we can save time, and I'll just explain it again once I've written that. Okay. The primary coil, as I told you, has alternating current flowing through it. It is therefore an electromagnet, and so it produces an alternating magnetic field. The core basically transports this alternating field to the secondary coil. Now secondary coil basically is a conductor moving in a changing magnetic field. So a current is induced in the coil. That is how a current is induced in the secondary coil. Okay. So moving forward, a setup transformer has a turns ratio of 1:20. The voltage across the primary coil is 12 volts. Calculate the voltage across the secondary coil. So we have a formula for that. Vp over Vs, that is voltage in the ratio of voltage in the primary of the primary coil to the voltage of the secondary coil is equal to the number of turns in the primary coil to the number of turns in the secondary coil. So Vp we know is 12 volts. Vs we don't know and have to find. Np obviously is 1 and Ns is 20. So we cross multiply everything, and 12 into 20 is going to give us an answer of 240 volts. So the secondary voltage is 240 volts. Moving forward, the power lost in cable is 1.25 into 10 raised to the power minus 3 watts. The resistance of the cable is 0.050 ohms. Calculate the current in the cable. So we can find that by the formula power is equal to I square R. Power has other formulas like power is equal to VI. Power is equal to V square over R as well. So here we are going to use this. We know that power is 1.25 into 10 raised to the power minus 3. I square is something we are finding out, and this is 0.050 ohms. So dividing 1.25 into 10 raised to the power minus 3 with 0.050 is going to give us an answer of 0.025 amperes. But this is I square and we need I, so we are going to put a square root on both sides. So now I is going to be 0.158, or we can round it off to 0.16. So the current is going to be 0.16 amperes. Okay. Moving forward to part C, state two advantages of high voltage transmission. Obviously, if we are transmitting at a high voltage, the power loss is going to be reduced. And the other advantage can be we can transfer energy over longer distances. There can be other as well. If you know another one, you can write that as well. Okay. Okay. Moving forward to question number 8-10. Question number 10. Define a light year in words. Okay. Basically, light year is the distance traveled in space by light in 1 year. So that is what we are going to write over here. So it is the distance traveled by light in space in 1 year. Moving on to the part B, it takes light 490 seconds to travel from the sun to the earth. Calculate the distance from the sun to the earth. Okay, we know that the formula to calculate distance is speed is equal to distance over time. We know the speed of light to be 3 into 10 raised to the power 8 meter per second. We have to find the distance, and for time we have 490 seconds. So 490 into 3 into 10 raised to the power 8 is going to give us a distance of 1.5 into 10 raised to the power 11 meters. So this is a very simple question. Okay, part C. Figure 10.1 is a scatter graph showing how speed of galaxies moving away from the Earth varies with their distance from the Earth. Okay. A scientist draws a best fit line on the scatter graph. Use this best line to determine a value for the Hubble's constant. Okay. First we should know that what is the Hubble's constant. It is H naught is equal to V over D. Now what is V? V is the speed of galaxies moving away from the Earth. So V is speed of galaxies moving away from Earth. And basically D is the distance of galaxies from the Earth. Okay, so if we look at the graph, there is speed of galaxy on the y-axis, and there is distance of galaxy from Earth on the x-axis, but there is this 10 raised to the power 4 and 10 raised to the power 20 over here. So if we are taking this point, for example 1, so let's draw the lines over here. The corresponding point of 1 is going to be, I think, 40. Yeah. I'll just extend the line so that they meet up over here. Okay. So this is the speed of galaxy. When this is the speed of the galaxy, then the distance of the galaxy from the Earth is 40. So what are we going to do over here is, so we basically, the speed is 1 into 10 raised to the power 4, because they've mentioned it over here that whatever this is, it is multiplied with 10 raised to the power 4, and whatever is on the x-axis, it is 1 10 raised to the power 20 times of what this is written over here. So this is going to be 40 into 10 raised to the power 20. So this is going to give us an answer of 2.5 into 10 raised to the power minus 18. Okay, so that is how we calculate Hubble's constant. You can take any other value that you like from here. For example, you can take 2, okay, and take a corresponding value on the y-axis. I think it's going to be 80. If I crisscross them, yes. So you may take these two values. So 2 into 10 raised to the power 4 divided by 80 into 10 raised to the power 20, and you are going to get the same answer. ठीक है, तो you can take any value that you like. 3 नहीं ले सकते हम. 1 and 2 would be more appropriate. Okay, so that is how we calculate this. Okay, D. The speed of receding galaxy can be estimated using redshift. Yes, this is very true. Describe what is meant by redshift. So basically, redshift is the increase in the wavelength of electromagnetic spectrum, yeah, electromagnetic radiation. So how do we describe it? That let's write, let me write the answer and just come back, and then you can read it because it's going to take some time. So this is describe and not just define. So if it was define, you would have written redshift is the increase in the wavelength of electromagnetic radiation, and that would have been fine. So when they ask us to describe, so we also have to write, so an increase in the observed wavelength of electromagnetic radiation from a star or galaxy because it is moving away from Earth is redshift. Okay, so this defining it to be the observed wavelength of electromagnetic radiation from a star or galaxy because it is moving away from the Earth is redshift. This has to be written so that it gets described and not just defined, because if you just define that, you are going to get 1 mark for it and not 2 marks for it. Okay, so this is it. Moving on to question number 11. Define the half-life of a radioactive source. So basically the average time taken for the half of the atoms in a sample of a radioactive material to decay is half-life. So it is the average time taken for half the atom in a sample of radioactive material to decay is half-life of a radioactive source. Okay. Part B. A protactinium nucleus decays into uranium nucleus by the emission of a beta particle. Complete the nuclear equation for the decay whenever there is a beta particle decay. So we know that the nucleon number remains the same, whereas the proton number gets increased by 1. So what we are going to do is that this is going to give us uranium, and it is going to have 234 and the what do you call it, proton number to be 92, and obviously a beta particle has also been emitted, so 0 and -1 is going to be here. Achha, just let me change this. It looks like chlorine, so let's write a clear-cut U over here so that it represents uranium. So this is it. Okay, moving forward, state the change that occurs in the nucleus during the decay. Okay, this change would be that a single neutron basically has split into a proton and an electron. So we can write that a single neutron has split into a proton and electron. Okay. So part C, a different element decays by the emission of alpha particles. Okay. Give two reasons why alpha particles are more strongly ionizing than beta particles. Okay. Alpha particles are more strongly ionizing than beta particles because they have greater charge. Number one. And number two, they have more kinetic energy than beta particles. So we can always write that alpha particles have greater charge than beta particles. That is why they are more ionizing. And second can be that the beta particles move faster than the alpha particles. So that is why alpha particles are more ionizing. What is the reason for it is that alpha particles, when they move slow, they are, by the way, the slowest of the three radiations. Like they are slower than beta as well as gamma. So when the alpha particles moving slowly collide with air molecules, so they may knock an electron from the air molecule, so that it becomes charged. The alpha particle lose a little bit of this energy, and it must ionize thousands of molecules before it loses all of its energy and comes to a halt. So alpha radiation is the most strongly ionizing radiation, and the reason for it is that it moves slower than the beta particles and as well as the gamma particles. So you may write these two reasons. And I think this was the end of the paper. Yeah, so we've reached the end. I hope you understood a few things from this explanation and this paper solving, and best of luck for your exams and best of luck for your studies. If you found anything helpful in the video, kindly remember me in your prayers and like and subscribe the channel for many videos that come your way. Okay, Allah Hafiz and take care.